Welcome to a lesson with Dr. Powell. Let's look at a little animation of what happens when we multiply two imaginary quaternions together. That means quaternions that have no real part. We're going to take one of these quaternions to have a length of 1. So that means when we look at its components, suppose it's like a plus bi plus cj plus dk, then if you take a squared plus b squared plus c squared plus d squared, this, and you square root it, that's the length of the quaternion, and that'll be 1. Now in this case, actually there's no real part because it's imaginary. So it looks like this, just the length in 3 dimensions. So the length in 3 dimensions that we see will have a length of 1. That's where we're going to start. Now we're going to multiply in quaternion land. We're going to multiply by the conjugate of u, meaning we make the imaginary part negative. Well, the whole thing's imaginary, so we just take the negative of the whole thing. So we're going to be multiplying by negative u, thinking of u as being a quaternion, and we can think of v as being a quaternion. So we're going to multiply by negative u, and we're going to do it on the right side. And that's actually important for quaternions because the multiplication is not commutative. So we're going to multiply it on the right. And if we multiply u on the right, actually what that does is it rotates things, and it actually sends u down completely so it lies on the real axis. So this is a little picture right here of imaginary dimensions. So u and v in 3 dimensions are going to be apart, but yet if we look at kind of a picture between imaginary dimensions and a real axis in comparison, they would like both lie on the imaginary dimension part. If we're just thinking of the absolute values of these things and just kind of putting it in this 3 dimensions into this one line, this is kind of what we would see. But this part right here is actually going to, in the rotation, is going to rotate down and going to be completely real. And over here in this picture, you won't even see it anymore. In other words, in 3 dimensions, in the real part and the imaginary part, this will be completely gone. Now, what happens if we multiply negative u times v? What's going to happen? It's going to rotate v. In this rotation, it's a 4-dimensional rotation. We're going to lose some imaginary dimension, and you're going to gain some real dimension in there. So as v rotates itself, we're going to v over here, it's going to lose some imaginary, it's going to gain some real. So we'll actually kind of see in this picture, we'll actually see what happens with v. We'll actually see the how it compares to imaginary versus real. So it's going to be shorter than v here as it rotates, but it won't go to 0. It'll still retain some imaginary dimension here. Let's kind of see what happens. All right, let's go for it, and then we'll watch this little animation here. Just a second here. All right. So let's go for it. All right, see what just happened? Let's repeat that. Okay. So in this process, go again. So it's rotating. So see what happens as it goes. Comes here, and as it rotates, so they're rotating, right? And notice as they come out of, so their main angle is all the way in imaginary land. But as we come down, as we rotate, the angle becomes more and more visible as we compare imaginary to real. In fact, because u rotates all the way to be real and not imaginary anymore, and v, okay, so then as you compare it to v right here, actually this angle right here is the same angle that we started with over here between u and v. So we actually can visualize this angle now as we compare imaginary to real. We've kind of rotated the picture between V and U, so we're actually comparing it via an imaginary to real comparison right here. As it rotates down, this is a 4-dimensional rotation. So as you rotate, you lose some in the imaginary dimensions, but you gain the sufficient amount in the real part so that it actually maintains the same length overall as a quaternion or as a 4-dimensional type object. Yet we can't visualize that, so we can look at the different components, right? We can kind of visualize what happens in 3 dimensions, and we can visualize what's happening as we compare imaginary to real. Let's take a look and kind of see what's happening here. We can kind of rotate in this animation our viewpoint and see. Notice what V has done. V has actually ended up being completely perpendicular or orthogonal to both U and V. So the image of V. So where V has actually landed in this rotation. It's in this four-dimensional rotation by multiplying by negative U, which has put U completely on the real axis, has actually brought V itself to be completely perpendicular to both U and V itself. In fact, we see in the process, let's just run through this. Notice that U itself is rotating, so the red is rotating 90 degrees, or kind of, it's an orthogonal rotation in 4 dimensions. So U has come down and rotated out and, to this point, and that seems rather orthogonal. In fact, this should make sense if you think about the multiplication of quaternions. So let's take a look at that for just a minute. So we're multiplying by negative U, and negative U is completely imaginary. So it's made up of something times I plus something times j plus something times k, and you're multiplying it to a whole thing over here. Now let's just take this. If we multiply it by this, what does multiplication by I do? That's an orthogonal rotation, meaning a perpendicular rotation. It kind of rotates everything by 90 degrees because to move the real axis from here to I kind of moves everything else in tandem or sequence around, so that everything kind of is like 90 degrees from where it was before in some way. But there's multiple ways of going 90 degrees in so many dimensions. As well as the same thing happens when you multiply this times all of that, or this times all of that. And then if you add orthogonal, which means in multiple dimensions, it means perpendicular. If you add these orthogonal results, you're going to get something that's orthogonal. You're going to again get something that's orthogonal to the original. And so the outcome is going to be completely orthogonal to where we started. So V, so this guy right here is going to be 90 degrees exactly from where we started over here. Just like this guy right here, completely real, is actually 90 degrees away from where we started right here. So this guy is orthogonally 90 degrees away from this guy. And now let's use an analogy to understand, or at least to visualize. And computationally, it's not too hard to see if you think about dot product and what it means to be orthogonal with that. However, let's just kind of think about a visualization conceptually for why this guy right here should be orthogonal to this guy. So why in the imaginary dimensions is kind of the projection of this guy to the imaginary dimensions still orthogonal to this, if we know that this guy right here is orthogonal to where it started right here? It has to do with the idea that V itself originally was purely imaginary, and we're going to use that idea. Let's suppose that we have a vector coming off of a plane. So let's just think about a three-dimensional analogy. Okay, so we have a plane, and we have some vector coming, maybe starting here and going off the plane. And then you know that it's perpendicular or orthogonal to some vector in the plane itself. So maybe there's a right angle between this vector, and maybe that vector, which is maybe another one for visualization's sake. Okay, so yeah, but just so you can kind of maybe just draw that again. Okay, but anyways, kind of imagine maybe kind of like this. So kind of think of a little plane section right here. So this is a 90-degree angle between these two. This is coming off that way and that way. So that's kind of like what we have here, because we have some vector coming off of the imaginary dimensions. And it's going to be orthogonal to something in the imaginary dimensions. This v, just like this is going to be orthogonal to something here in this plane. Now, the question is then, if we take this guy and project it onto the plane, so this vector right here, when we project it onto the plane right here, look at its part in the plane. That's just like taking this vector and projecting it to this part in the imaginary dimensions. This is the part of this in the imaginary dimensions, its projection onto there. Notice in this picture that this guy is orthogonal to the original vector, just like this should be orthogonal to that guy. Well, in 3 dimensions, this is kind of simple to see, because what's orthogonal to this is like there's a whole plane of things that are orthogonal to it. And in order for this to be orthogonal in general, it has to be in that plane, and its projection is going to be a line which is perpendicular to this guy in the plane. So the same basic analogy actually gives us that we know that this guy from an orthogonal operation is going to be orthogonal to the original, which lies in all, in these imaginary dimensions. And this is orthogonal to that. Its projection onto there, these imaginary dimensions, is going to be orthogonal to this guy as well. This is this analogy. Now, if you think about dot product, if you accept the idea that if you take the dot product between two things, meaning like if you have like so suppose, for instance, you have like this vector right here. Think of it as a quaternion. With 4 different parts, A, B, C, D. And think about, okay, and think about this guy, right, which is completely imaginary, as having a 0 real part. Maybe you have like an E, F, G happening here, okay? So things are orthogonal when we multiply like downwards the different components, like this times this plus that times that. So we can write that out. So A times 0 plus B times E plus C times F plus D times G. Okay, so in order for this to be orthogonal, this is 0. Well, notice that this A times 0 doesn't affect anything at all, right? Which means that we have the dot product of just these parts right here. It just suffices for that to be 0. So that's like, okay, in the imaginary parts, there needs to be an orthogonal condition. And that has to do because the original guy itself was 0 in the real part. Okay, so some analogies here, but what we get is not only does U rotate to something 90 degrees over from it, which is from completely imaginary to something real, but V will also rotate because as a complete 4-dimensional rotation, everything kind of shifts the same way. But we kind of talked about some ideas why we can see that V also rotates. And not only is its part right here 90 degrees or orthogonal away from the original, but the projection itself in the imaginary part is also orthogonal to it. So we get that the result of the quaternion multiplication, if you project it into the imaginary part, in the imaginary land here, which is the 3 dimensions what we experience, then the result is actually orthogonal to u and v. Let's take a look now and see how to represent this between cross product and dot product. Okay, so it's actually apparent in the animation itself. Notice here we've labeled these things. Now, if we're considering u to actually be a unit vector, then this is like the length of u is just 1, so you can kind of ignore this part. Just think of this as u cross v. If we assume u to be unit vector, you can just imagine this is just u cross v. So maybe I'll write that out. Okay, so you can just think of this as being, yeah, for our sake, we're just imagining that u has a unit length, so just u cross v. And all right, see what u cross v is? It's actually the length of the projection of this guy v, the image of v after the rotation. So this is after v has been rotated. This is before v is rotated. This is after. So maybe like v after, okay. So if you take v after the rotation and you look at its the absolute value or the length of the imaginary part, that's what the cross product, that's kind of what we're looking at, the cross product. In fact, it's not just the absolute value, it's actually the imaginary part itself. It's the whole imaginary part, because u cross v is a vector. It actually lives here. It's not just a number, it's actually a whole vector. So the projection as a vector itself into the imaginary parts is the cross product. The cross product will naturally be orthogonal to where we started at v. And if you can look at this both ways, because if you reverse this like v times u versus u times v or whatever you do, or if you have negative u on one side or the other, or whatever you do there, you put v or whatnot, it actually just changes the sign and the direction. But you still get that whether you do that, u cross v is actually going to be orthogonal symmetrically to v and u, to both of them. Okay, so that's what the cross product is. It's just the imaginary part, of the after effect of the rotation. You just project it in the imaginary dimensions, and that is the cross product. Now, what's the dot product? The dot product you don't even see over here in 3 dimensions, and the reason why is because it's completely real. It's sitting over here. The dot product is actually, so it's just a number now because we're just considering it as a real number. A scalar, this is kind of like a scalar axis. So scalars are like the 4th dimension, but you don't see or visualize them because we're sticking on the 3-dimensional imaginary part over here. But it's actually the projection, and you can even think of it as a vector projection if you think about a real number as being a, or a scalar as being a vector, onto the real axis here of the after effect of v after the rotation. So u dot v is going to be this part, and u cross v is going to be this part coming up and down. Okay, so what we end up getting is kind of a neat idea, is that if we allow ourselves to pop over into imaginary dimensions, we actually or and a real dimension with a real dimension, then we get a nice triangle where we have u dot v for a length over here and a length over here. So you see this red? This red is actually just the image of u after the rotation. It's in the same line as the real axis, but it's not the same thing as the projection of the after effect of v. The projection of after effect of v is actually this whole bit from here to here. So it's actually a little bit bigger. So you can kind of ignore that red if you want. It comes all the way out to here. That's what u dot v is, and u cross v is going up and down. So we actually get, hold on, u cross v. So u cross v is this part, u dot v is that, and we have a triangle. You can even use this triangle if you wanted to analyze the angle right here. But usually when we're finding angles, we don't really think about the cross product here. We just use the dot product because we already have this length. We just take the length of the vector to begin with. because this is really just the after effect of V. And if you want to just think of length, you could just think of length there. You could just think of the length of these things if you want. In a triangle, you can use a cosine right here, and you can get the angle very nicely of between the two vectors, because all we've done is we've four-dimensionally rotated this so that we're kind of in this position over here, and we can have the different lengths. So I hope this little visualization and animation helped a little bit in understanding what quaternions do when we multiply by with them and how they relate to vector operations, the dot product and the cross product. Thanks for watching.